welcome everyone, and today we are happy to have a talk by Euihun Joung, and he will speak about color particles in low dimensions.
Let me try to share the screen. Yes, good. Maybe like for the talk. Okay, thank you very much for the invitation. Yeah, it would be nice to visit Moscow, but yeah, this time, yeah, I heard about this new institute, but anyway, yeah, it's good, great pleasure for me to give a talk there. And it's yeah, on my today. So today I will talk. The title of talk is colorful. Particles and fields in low dimensions. This is the title of my talk. So actually, yesterday there was a seminar by one of my collaborators. So I assumed that actually Mitya told me that the audience will not overlap, but I assumed that it may overlap a bit. So I tried to make make my talk as complementary of the yesterday's talks. But I hope that the one who didn't listen yesterday's talk can also enjoy my talk. I hope so. So here the organization I made in this way. So I will just begin with these questions, whether we can extend or generalize space-time symmetry with the color. So color extension of space-time symmetry. So extensions of space-time symmetry was this question was considered by many authors historically. And in this way, somehow we discovered the supersymmetry. Also, you know that Coleman-Mandula theorem, and also, in a sense, higher spin symmetry is also an extension of space-time symmetry, which includes the symmetry corresponding to many higher spin states. In fact, this color extend. And then the questions in this talk is whether we can extend the space-time symmetry in a way that it is somehow addressed with the colors. So typically, we have a space-time symmetry and then just the direct multiplications of internal symmetry, and they are in a sense separated. But in this talk, we want to somehow extend in a more non-trivial manner. Actually, this kind of extension was considered in the context of higher spin symmetry by Vasiliev. And in a sense that we take those ideas and then apply to more, in a sense, simple model. And then first build this color extensions of space-time symmetry, and then apply those symmetry to various models. And then today I will talk about the few applications that I have considered with my collaborators. Yes. So to begin with, let me first just we can begin this way. So say that the space-time symmetry is given by is generated by generator X, and then color symmetry is generated by generator Ti. Then the question is that whether we can have space-time symmetry which has also color index. In a sense, we want to make U symmetry generated by something like XAI. So in this way, suppose that we have typical translations and rotations. Then if we add some additional index, actually that will lead to the multi-gravitons theory. That has been known, and then that kind of thing has been studied by also many authors. And then several no-go were pointed out, and also some exotic, some kind of yes-go has been also studied by different authors. But here, let me show one key idea behind the no-go and also yes-go. So if we take this new symmetry generator XIA and I as a simple product between these two generators, then typically this will not work, because if we want to calculate a Lie bracket or anti-commutator, commutator, then I mean, with the usual rule, you can find that actually it's given like this. So here, from this equation, you can see that even though that we have put Lie algebra structure in both space-time symmetry and color symmetry, this direct multiplications of two symmetry cannot give a Lie algebra unless we make sense of this anti-commutator. Yeah, so this anti-commutator is important. So in a sense that, so here the lesson is that if both space-time and color symmetry can be extended to an associative algebra. If each of these symmetry can be extended to an associative algebra, then both commutator and anti-commutator, both commutator will make sense. So in this way, we can make sense of these expressions. Yeah. So then this will be. So this will be yes-go. So in case that we cannot extend our space-time symmetry to an associative algebra, then we can interpret this as some sort of a no-go. So that's why actually higher spin symmetry was a natural object. I mean, it was relatively straightforward to extend higher symmetry to colored versions of it, because we know, as you may know, most of higher spin symmetries has associative structure. So in this talk, we will just consider the simplest possible space-time symmetry and also color symmetry, which can be extended to associative algebra in a simple manner. So that is the ADS2 symmetry, which is O 1,2 isomorphic to SL2R. SL2R is nothing but clearly 2x2 matrix, but traceless condition is imposed. So we can just remove these conditions and we can take GL2R. Then it's just 2x2 matrix. So it has clear associative structure. So we need to add one more generator, which is actually identity, to have this extension. O2,2, this is 2 copies of SL2R. So this can be also extended GL2R plus GL2R. So this is a kind of minimal options. And then another minimal option would be probably ADS5 algebra, which is isomorphic to U2,2. That can be also relatively easily extended by adding just one generator, which is identity. But all other space-time symmetry can be in principle extended to associative algebra by adding more non-trivial generators. That's simply by just you suppose that you want to consider O2,D, then just you embed this O2,D inside of GL2R, GL and R, or some other associate algebra which is associative structure. But that will clearly have way more generators than just identity that we added in this case. Okay, good. So this is the setting, and then color symmetry. We will use all the time UN, which has also associative structure. So in this way, we essentially take direct product between GL2R and UN, and it turned out that this is nothing but actually UN, N. So in this way, actually, we see that we can interpret UN, N, this typical Lie algebra, Lie group, as we can interpret it as a color extension or color generalization or Taylor equation of space-time symmetry. Space-time symmetry, O1,2, ADS2 symmetry. So in case of ADS3, you can just consider UN, N times UN, N. It's a colored ADS2 symmetry. N. So this is colored ADS3 symmetry. So now, since we have this UN, N, we can try to see that some how the generators of UN, N can be somehow arranged. And I just sketched very simply that actually the generator will have form like that, XA and then T, so that it has both index. But actually, there is a slight, a bit more than that, because we added the identity to make each of these algebra to associative ones. So actually, we added the identity on top of space-time symmetry generators, and also identity on top of the color generator. So in this way, if we just expand these guys, we see that there is identity times identity, and then plus, plus XA times identity, and then I times TI, and then there is this colored guy. So this is nothing but, again, identity, which is actually U1 of UN, N. Actually, if we construct anything out of UN, N, actually, we have considered Sun-Simon formulation as well as BF formulations, and also some particular consideration. In all those cases, we have considered SUN, N by removing this U1, because that were sort of decoupled all the time from the other. So this was original space-time symmetry. And this is color part. And this is somehow the new exotic guys, which is colored space-time symmetry. Yeah. And then this is space-time. This part is space-time symmetry. So this, if we make, suppose that if we make gauge theory out of these algebras using first order formulations, we will get gravity. And these guys will give some sort of gauge field. So if you like spin one. On the other end, this guys has both color index and as well as space-time structure. So in this way, this gives colored this into quote-unquote messless, because we will consider also a two-dimensional case where messless, the meaning of messless is a bit unusual. So okay, so this is the general structure, and then we will apply those things to several different models, applications of this color symmetry. And then the first thing was the Chern-Simon formulation of 3D gravity that you know well. But if you replace usual SL2R by UN, N, then or SUN, N, then this will be nothing but 3D colored gravity. So this is the work that I did first on this topic with Guap and Christian, Karapet, and Sujong. And then there are also, I also studied the asymptotic symmetry related to this with a different observer. So this was some few years ago, so relatively old story that I will not talk today. And today I will talk more the recent, relatively recent thing that I did, which is the applications of this symmetry to constructions of world-line particles. So this is done with the Gomez and Sarah Klein-Smith. And the Christian. And then recently I did also BF formulation of say 2D colored GT gravity. That was with your colleague Akalaev, and then Yun, who is in Korea. And we did it here. And then in particular in these constructions, we recently it was sort of a hot topic that this static gravity, reduce static gravity to Schwarzian and then quantize Schwarzian and then do many related work in the context of this quantum gravity and black hole paradox. So and then what we have done is that we also tried to we obtained the Schwarzian-like reductions of these BF formulations of 2D colored static gravity. So these two parts I will try to explain in the remaining 40 minutes, probably something like 15 or 20 minutes, less than 20 minutes on these topics, and the other 20 minutes on this topic. I hope that I will have sufficient time. So first, world line particle action from this SU UN comma n. In that way, we will get some sort of weird color decorated particles. So then for that we need somehow more general scheme to do that job. So how we can approach? So we need to understand first how a symmetry or Lie group can just dictate the word-line particle actions. So this is, in a sense, well-known subject. So quasi-in orbit of a given symmetry group is associated with some particle, or if you like, representation and particle species. And then using this quasi-in orbit, which is actually symplectic space, we can construct word-line particle actions. So actually, it's just advertisement is that I'm also working on more general treatment on this topic with my collaborator, Basil, and also Tevan. So this is all topic, but nevertheless, many things are relatively less understood, or in this community, we have impression that it's not widely spread, and then so we decide to summarize things, and also we point out some new aspects in it, but that will be probably in a few months. Ready in a few months. So now, let's take first the example how we can obtain a typical word-line particle action from merely from this symmetry treatment. So we know that. So how to write down a massive scalar particle in flat space in Minkowski dimensions. So this one actually the particle action that you all know can be obtained actually straightforwardly, or just straightforwardly by plugging the symmetry as Poincare symmetry and choosing the orbit to the relevant orbit. Then actually the procedure just dictates the action that you should get, and that in the end you can check it coincides with the typical the standard action that you all know. Let me sketch it quickly. So Poincare symmetry is spanned by translations, then Lorentz generator. I should check whether I have enough time to talk all these details. Then the dual, because it's a quasi-in space, which is just the dual space of this Poincare algebra. And then the dual basis I will write in terms of this tilde variable. And then the quasi-in orbit, since it's an orbit, can be just identified by a representative vector, any vector in the orbit, if you like. So just we need to pick up one particular vector in this quasi-in space. And then typically this phi can be just a vector in it. So we have a component like this. So this is the component. And then by choosing specific vector, in a sense, or in other words, by choosing specific components, we take one specific vector, and then that will specify the orbit. And once you specify the orbit, then the word-line action will just follow from it. So the usual massive scalar particle actually is associated with corresponds to the choice 5 is m p0, or if you like, in this case, p mu is m0, 0, 0. So by that you already have an idea that okay, that massive scalar particle, I mean, it has the momentum shell has this shape, and then canonical typical this momentum vector has m0, 0, 0. So indeed, it has the same kind of idea. But here, just need to know to have in mind that actually all this thing is embedded in the dual Poincare space, and then J part is also 0. And then the action is just so it can be obtained from the usual well-known treatment, constant Kirillov-Sohio, that the symplectic structure can be. So we know how to extract this symplectic structure from certain quadrant orbit, and then so that tells us in the end that anyway the action will can be just take this form. So here this bracket is the algebra, and then dual of the algebra. This to dual, the bracket related to the duality between space and dual space. And phi is this vector in this dual space, and G is this Moran-Cartan. It gives Moran-Cartan element, and then G is the Lie group element. So Poincare group element, and which we can parameterize like this way. First the translations, and then boost, and then rotation. Then I will skip the detail, but if you just compute blah blah da 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 da, and just plugging it and compute da 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 da, then what you would get is this one. So actually this part is just the drops, and then this part, when you take differentiations, if you act this part, the J appears, but the phi is only on the P side. So again, this will essentially not drop, but it will, and you have a limited role. And then anyway, in the end, we get like this, because the actions, so P, so this is adjoint action on this side, can be transported to coadjoint action to the other side, so by definition. So we, using that rule, we can just write this way. So in the end, this derivatives acts only on the first part, and that's why we get this one. And then in this way, what we can see is that actually this one is just boosting this typical momentum, which is taking this value. So in this way, so this is nothing but another momentum, but in a way that which is actually P mu. P mu is m squared, because this boost will move to this vector, to any vector on this surface, which is actually write down 0 is positive. So 10 minutes. Okay, so I should accelerate. So, and then so we have this square root p square m square, and then px0 and pi pxi. So we just have this. So at this stage, the action is given by x, which is variable of these actions, and then v is another variable of these actions. But v is parameterizing this surface, so we can just change variable with the pi. So that's why I can write in this way. But what we can do more is that we can replace this section to the typical one, p mu dx mu, and then this mass shell constraint can be just imposed by constraint. So this is in this way, constraint system. So this is in a sense more neat and more, but actually this is not completely equivalent passes from this section to the other one, because by doing this, actually we just drop this part, positivity of. So originally we were considering only this orbit, upper hyperboloid, but by replacing the direction in this way, we also included the lower hyperboloid. So we have these two. So this aspect is somewhat becomes more interesting in color extensions that we will discuss now. So colorful extension. Again, the symmetry is originally we have, so we are talking about 3 dimensions. So Lorentz has also one index after dualizations. And then we have mu, so just the usual graviton part, and then the space-time symmetry part, and then there are also other color pattern, and then the mixed part. So we have this much of generator. And here color extensions, we will take, I will not discuss more, but flat contractions action of u n comma n times u. So this is what we did in the paper, the contractions of this algebra, or this is symmetry. But also we did uncontracted ADS particle. But the flat space particle is easier to interpret and understand the kind of non-trivial aspect that this model has.
Sorry, can I ask one thing?
Yes.
Yes. Can you construct in this way, in general, the point particle action in the Young-Mills background?
Young-Mills background.
Yes. Like color spin 1, but in general D.
Color spin 1 in general D. So what do you mean? So you mean this quadrant orbit method, or
yes, whether it makes sense, to speak about this. Can you couple a particle to a point particle to a Young-Mills background?
So if you are asking whether we can get the particle action with some backgrounds, non-trivial backgrounds, so those things can be obtained from quadrant orbit method, then I don't think so. But maybe there are room to extend the quadrant orbit method in such a way, which I'm trying to think and work on it, but for the moment, I don't think it's no.
Okay, thank you.
Yeah, so our aim is much more modest in here. So here, actually the motivations of Gomis and Joachim and Axel, and also Karapet was, so they wanted to somehow revisit this Wang equation, which is some particle which can couple to Yang-Mills. So we all know that how to couple the usual particles to just electromagnetism, just like relatively easy treatment. But Yang-Mills is a more non-trivial. And then there was old work by Wang, who elaborated this point a bit further. And then we wanted to revisit they had some motivation to revisit it, and then this looked like some possible candidate, but actually it was not exactly doing that kind of job. So we are obtaining some sort of I would say exotic particles, which can couple in a sense, if you like. This particle can couple not only Yang-Mil but also colored spin 2. So the gauge sector is gravity, Yang-Mil, and colored spin 2. These colored gravity guys, those guys will can the couple to this kind of particle that we are considering.
Mm-hmm.
So anyway, the construction is coming back to the story. So we need to take first an element, the quadrant space. So this is not good. So say G star, because it's contraction, so it was not good to in that way. But anyway, the choice is the same, because anyway, so this generator contains the usual translation part. I take the same guys as the representative vector, but this can form more non-trivial orbit, because we have you don't have just Poincare, but also many other generators. So the other generator can act on these guys in this vector, and then the orbit will become, I would say, rich or more non-trivial. So, and then it's straightforward to do the job, though it's a bit, you need to go through a bit lengthy computation. And we can obtain some formula which I will not present to you. But anyway, it works, and then you can obtain what you can obtain. It's precisely the analogous expressions as this or this. This kind of thing we can obtain. But probably it will be better to directly go to this kind of a nicer setup. So the question is whether we can get constrained action. And then the answer is yes. And then the action is look like this way. It's a trace P x dot plus L G square minus N. And here x and P is SU n comma n elements. So it's 2n by 2n matrix, if you like, and L is U n comma n. It's also 2n by 2n matrix. Yeah, to understand how it works, we can first take n equal 1 case, which is uncolored one. Then actually the action boils down to simply so maybe I will not write down. So here P is 2 by 2 matrix, X and P. Right. With n equal 1 is 2 by 2 matrix, and then L is turned out to be just its proportional to identity matrix. So in this way, we get the action which is look like 2 by 2 matrix P x dot plus E, and then P square minus M. But since we are working in 3 dimensions, you can see that actually this is nothing but exactly P mu P mu plus E P square minus M. You know that P square in the vector form can be written in the matrix form like this P square, this way in 3 dimensions. I will not present the detail, but probably you have seen all these things, so I will not say more details. Anyway, so the usual uncolored 3D particle can have this matrix form. I mean, precisely this form can be rewritten in a matrix way, matrix form, but that can be uplifted to this form, like as you have. And then this will be actually the constrained actions related to this guy. So I'm saying related because I emphasized actually this is not identical to this one. So we need to somehow some sort of generalization. We need to include additional orbit to get this one. Here we have also same situation. So let's take n equal 2 case. Then what we get is that actually this sections has 3 orbit. The orbits which look like this one, which look like this one. I'm saying quote unquote mark because it's not exactly of this form, but we can think in that way. And then actually the original phi that we took was belonging to these guys. So actually these sections, if you just continue to work and then if you obtain something, it describes the actions corresponding to only this orbit. But the constraint system contains not only contains 2 other orbits, which is look like the lower hyperboloid together with other guys which look some. Again, this is cartoon image. It's not precise. This kind of orbits. So this one was the original guy P0, which is probably this point. And this can be written in a matrix form 1, 0, 0, -1. And then actually you can see that this phi, the typical element of phi probability here, is just minus sign. So which is -1, 0, 0, 1. Sorry. This was what I wrote. It was just uncolored case. Colored case is this one. But then this one is related to the middle one is related to actually 1, -1, 1, -1. So this is so more generally now in general. So how many orbits is included in this section is actually n+1 orbit. Related to phi, which is m, which is 1, 1, -1, -1, 1, -1. And then this is a half line. This is our n. And number of these guys, which is L. So L came from 0 to n. So it's all together n+1 possibilities. And then the dimensions of this orbit is 2n squared. Probably I should just keep, maybe I will just mention. So this orbit can be viewed as this flag manifold. Because any equation orbit is obtained by the original the symmetry and then just the quotienting by the stabilizer, and we can realize and we can understand it's like this. So I should probably skip other massless case. Okay, and then I should go to probably BF formulations and reduction to the Schwarzian. Maybe I was too ambitious to talk these two things one time. So I will try to maybe give a sense. Again, so now BF formulation, BF and then Schwarzian. So once again, in this case, like in the particle case, if we know the generality, then just we can replace, we can just plug in un comma n into the algebra, the algebra slot. And the BF theory is for any algebra, you can think it has this form. F is with the strength. And then there is also there should be also this boundary term together with the boundary condition. I would like to emphasize that this is not the only possibility, but this is a typical sort of common choices in the literature. So in the end, what we get is that okay, onshore actions is k gamma 2 on the boundary, trace a mu square. Because of this, but anyway, phi is proportional to a. Only this survives because this goes to 0 on shell. So it's not full on shell. Actually, we only use Lagrange multiplier equations. That's also important, but I should go a bit faster. So. And then eventually, what we need to do is that. So this is the action, but what we need to do more is that to solve f equals 0 equations and then plug into there together with the asymptotic ADS condition. So just we need to solve f equals 0 with these conditions, and then the solution we plug into this, then we get the reduced action, which is Schwarzian in the case of the uncolored case. So let me sketch how this can be done. So typically, once again, how we solve the equations. Again, we decompose this way. U p plus p1. P is this function radial coordinate, and then A is functions of U. So this is typical thing that we do in the Chern-Simons formulation. Probably you're familiar. So it has this form. So then, so it's yeah, the sort of case fixing, and then etc. will lead to this, and then f equals 0 will say that okay, A should be G. And then this boundary condition, asymptotic ADS condition. So this will say that okay, A should be L-1 arbitrary functions of U and L-1. So this is the generator of L1, L0, and so I will not give more detail about this commutator, but you can guess easily. And in the matrix form, so this will look like minus L. So this is in a sense, this is background, ADS background. And this is where fluctuation is. And in this way, we can see that a mu squared u is minus 2 u L u. So essentially, this L is appearing in the reduced actions. And then now it's we need to compute L together with these conditions. So for that, we do we can distinguish zero temperatures and the finite temperatures. In the zero temperature case, we use this Gauss decomposition. and then we compute A, and then equate this one, and then eventually what we get is L is actually B that's 2 inverse B double dot square, and then B square is F dot. And then in this way, so this, if you rewrite in terms of F, this is nothing but 1/2 of Schwarzian expression. Commit writing time. Yeah. So this is the story, the typical story. And we can also do the finite temperature case. So typically for the finite temperature case, people do this redefinitions of F in terms of tangent. So then L will be finite temperatures, 0 temperatures and non-zero temperature this way. And then that will be precisely of this form. And then there will be additional term before, and then here B square equal 1/2. And then we get this is 1/2 of the Schwarzian, and then theta and U plus 1/2 theta square. So this is what is called, what people call the finite temperature Schwarzian actions. That's all given by these redefinitions typically. But this kind of redefinition is a bit hard to generalize to other cases, like say like chiral spin or colored versions. So that's why we try to understand somehow reasoning behind all these redefinitions and behind finite temperatures and then 0 temperature and all this. And then the conclusion was that actually the Gauss decomposition itself is if you like, so this theta should be as U goes, this theta coordinate is clearly moving around this group manifold, but it should wind non-trivially this group manifold. That's the important part. So that was the important part for the finite temperatures. And in order to realize such configurations, what is better is that to parameterize this group manifold using maximal complex subgroup. Because so just a non-trivial diswinding, for that we need the fundamental group, and the fundamental group of a non-compact group is the same as the fundamental group of maximal compact group. So in that way, actually, it's quite natural to use and decomposition which makes use of maximal compact subgroup. So that's precisely what is Euihun decomposition does. This is cosine zeta 2 minus sin zeta 2. So then, so just we didn't do anything but just to take different parameterizations, and then we can check this is giving precisely the right non-zero temperature Schwarzian. This is all good. So then now, so we understand more or less the sense, and then we can apply this to the colored case. And then again, what we do is that, okay, color extension. For that, what we do is that, again, this A part, the way that we write A is the same. And essentially the difference is that how we should define asymptotic ADS conditions, because A has many more components. AU has many more components. It has this space-time part, but also it has other part which is JA, TA, color part. So, and then -1. And then the genuine so you see that so this part was the original gravity part, but we added other generators, but in a way that we avoided to use L1 of TA, but the other things we just put. So this is our color extensions, the color extensions of asymptotic ADS conditions. And this, if you like, in a sense that the only background is coming from color singlet sector. And then apart from that, everything is allowed. In a matrix form, again, it will be useful to write it in a matrix form, as in the case of uncolored case. We write down this way. And so this is J. And then all together, this guy all together, we write down L-1 times then the action that we have to calculate is given by trace L square term and then J square. There are two contributions, one coming from L, which look like color matrix extensions of the Schwarzian, and then there is other part which is J square. So here. Anyway, now, so just again the same game. We just take good parameterizations of G and then plug in to the game and then compare with this and then to compute everything. And then let me just write down the answers. And then it's a trace P minus 1, P double dot minus 2, P minus 1, P dot squared. So B is again a matrix generalizations of this B parameter that we had introduced in the uncolored case. Again, these are all matrix versions. And then here the condition is P square is F dot. So this is our formula. So this is reduced actions where D plays the role of spin 1, and the singlet part of B is genuine spin 2, and then non-singlet part of B corresponds to colored spin 2 part. And then yeah, we can interpret in this way. One subtlety is that actually we need to solve these equations, and in the uncolored case is we can just put square root, but now this is a matrix equation and it's more non-trivial. And then again in here we have many different branches of solutions that can be also viewed as some sort of different orbits. And then it's not yet completely clear, but that resonates clearly the multiple orbit stories in the particle actions. So my time is just over. So just instead of writing things, I'm just comment a few more things. So we can do also finite temperature case. In that case, we need to take another decompositions of this SU n comma u, sorry, group un comma n, sun comma n, which looks like Yazawa decomposition, but it's slight variations of it. And then again, it gives a good, reasonable form. And then, yeah, that I cannot write, but it has precisely the usual b to the fourth part in it, and also other additional expressions. Yeah. And moreover, we did also various analysis, linearization analysis, and also a rainbow vacuum, which means that actually there are other symmetry breaking solutions of these models. And then in Chern-Simon's case, we have shown that those will lead to the very interesting patterns of symmetry breaking and the Higgs-like mechanism. And similar things could be studied in these BF formulations. And then we have seen also some sort of Higgs-like mechanism, but in this case, it was rather strange. In the 3D case, spin 1 and spin 2 were glued together to form a partially messic spin 2. But in the BF case, we have seen that the spin 1 and spin 2 were glued and split the other way. In the end, we have only spin 1, spin 2, but somehow it's the rule was mixed up. So that kind of thing was observed. Okay, sorry, so yeah, so I'm done. Thank you.
Thank you very much. Are there any questions? Can you comment at the beginning? So you had this SUN, just UN, comma n, and then like you had 4 terms, like 1 times 1, right? 1 times x plus t times 1.
Yes.
Yeah. So these pluses, it's not like it doesn't mean direct sum, right? In the sense that it's not subalgebras.
Actually, those are subalgebra. So this UN comma n has 2 subalgebra. I mean, it may have more than 2, but spacetime symmetry is on subalgebra, and then this color part is another subalgebra. Yeah.
And can you?
So actually, that aspect makes it easy to analyze the actions of this theory somehow. So actually, just to tell the story, so originally when we studied this one, we first what we did first with the Karapet was Chubby interactions and Fortic interactions, blah blah blah, and that kind of bottom-up like approach. And then at some point we understood that it is much easy, there exists much elegant formulations. That's because we have 2 good subalgebra, and then we could make everything in the everything covering under these 2 subgroups. So that and then formulation become was much better.
Mm-hmm. But at least the one piece is an ideal, right? So you can quotient it out.
U1?
U1 piece, U1
yes,
term.
U1 can be just quotiented out. If and you write Chern-Simons on BF with the U1 and it just decoupled from the rest.
Mm-hmm. And the rest has to come together, so you cannot like drop other things.
Right, they are just tied together. Yeah. Mm-hmm. There are, so in a sense, this is 2 gauge fields. Actually, these guys and these guys, they don't talk to each other. Because this spin 1 is topological. Chern-Simons or BF are really topological. And then this is the gravity sector, and they don't interact. But there are sort of matters which are sort of gauged in both of these fields. It's gravitationally gauged, I mean, general covariance, as well as you engaged. So these two sectors can eventually talk through this matter, which is this spin 2.
I see. And in higher dimensions, you said that you still can do it, but you need to embed it into like larger, like still GL like D, right? GLD.
Yeah. So algebra-wise, there is no much problem. I say. In some cases, we have a much simple color symmetry, but in other cases, I mean, you can always by adding minimal generator, additional generator corresponding symptotic partially messy steps, blah blah blah, multiple copies, whatever. So that's after this, actually, what I understood is that probably say that SLN, SL10, say. So that can be interpreted many different ways. I mean, the different real form of SL10 can be interpreted in many different ways. Spin 10, higher spin interpretations, or if you take U5,5, then it's U5 symmetry, colored gravity. But if you take a different real form, I think then it will be just mixtures. There are few numbers of higher spins, probably not to 10, but slightly lower. And there are other fields, which is maybe multiple. And then, so it's all about how to embed or what kind of real form that you take. But, so anyway, so this algebra can be obtained in that way, constructed, but I'm not sure whether we can get reasonable theory out of the other algebra in higher dimensions.
But at least, so I got a bit confused. So you said there are different ways to embed the space-time algebra into that extension, or? And like, what kind of a gauging procedure are you going to use? You are going to write some sort of like Einstein-Hilbert action for it? Because for Chern-Simons, it's pretty clear, right? It's you just extend the indices, they take values in different algebra.
Right, right. So in a sense, that's maybe that reflects the problem. In higher dimensions, there's no obvious way to use to obtain the actions merely solely from the algebra. So we always need some other fixing procedure, or we need some additional surgery, and that will probably spoil the consistency. And I have some argument that most of the case probably will have problems. Maybe some topological theory can avoid the problem, but otherwise. Okay, so the argument is actually based on what is called GK dimension. So actually, if algebra is too large, then we always need infinitely many fields. Because if algebra is too large, then the kind of phase space that it can accommodate cannot be too low. So there is this correlation.
Because it should be a representation, right?
Yeah. So that put quite severe restrictions.
I see. Any other questions? Okay, since we don't have any other questions, thank you very much for a nice talk.
Okay, thank you.
And yeah, this was the last talk this semester. So have nice vacations.